topic of development of an automated text-based interdisciplinary classification of projects and publications using NLP. Well, this is a mouthful, and we'll get through that today. As always, we'll share our slides afterwards. If you don't, please follow us on all our channels. We're happy about everyone who follows. Now, we are a project in the Berlin University Alliance, as Fatwa has already mentioned. And as such, we aim to achieve a multitude of goals. The classification is a narrower project, but we still follow our main principle, namely to produce a software that is as automated as possible and produces as little strain on our researchers as we can. As you see here, we are still developing our Vivo platform itself. It's, as of right now, in closed developer mode. I would like to focus your attention on the right side, namely the charts that make Vivo so great. We have the co-author network, we have our publication charts, but one of the main charts is the map of science. The map of science comes with Vivo. It classifies every journal article in, well, this, I really like it, great visualization, but it comes with a lot of drawbacks. Vivo is an open science platform, and we love Vivo for it, but this specific part of it isn't open science. It's hosted by Elsevier, and as that, it only can fulfill a very specific role. Namely, it only classifies articles when they're connected to journals in Vivo, because it has a database of journals. It cannot classify anything else, which is kind of sad because we have so many great publications in Vivo which we cannot classify, we cannot link, we cannot match. And a second problem that comes with it is that because it's a proprietary software, it's not really linked to the Vivo ontologies. Our goal is to fix that. So that's why we partnered with a company called Kerntech, specialists for machine learning. Stefan Geisler is here, I'm very happy. That helped us with developing pipelines and machine learning models to classify texts and projects. And as you can see here, we already integrated that here on the left side into our tech stack. So what we're doing right now is before we send our cleaned data into the Vivo, we can classify it now, and we can send classifications with our data. What challenges did we face? Well, when we started the project, the first idea was, can we classify everything? And the answer is simply no. What we need to classify anything is text, and we find text usually in publications, but also in project descriptions. So those are the two main units we're focusing on. We try to use large language models and machine learning to analyze the text, to categorize, and at the later stage, to link our results. To do that, the first step was to find an actual classification we can use. We talked to a lot of experts in the field, and we came down to two vocabularies we want to use. One of them is the so-called EU.B2Find vocabulary. It's a European, it stems from a European project, so it's a European-wide classification, and it is a disciplinary classification. That means it classifies specific disciplinary fields in science. The second classification we took a look at is the so-called interdisciplinary research fields classification of the Kerndatensatzforschung. We did some tests with it, but today in our talk we want to focus on the EU.D data. The EU.D disciplines, as you can see here, are not a simple task. We have a 4-layer hierarchy which gets more deep and more complicated and more precise as you follow the hierarchy down. It has 5 main categories. And as you can see here, those categories are filled to the brim. We have 336 categories total. Now that we decided on how to classify, we still needed something to actually classify, because if we want to use machine learning, we need a data set we can train, we can develop our models on, and we can at the end use to classify the actual incoming data. Gladly, we work at the Humboldt University, and we have an open source eDoc server that provided us with about 20,000 documents to use. This corpus doesn't come without drawbacks. As every researcher can publish their work there, it is a pretty unbalanced corpus, which means not every category is represented equally. It is very heterogeneous, and it comes in various languages. It's a multilingual corpus. We still tackled the challenge of approaching this corpus, and we tried to assign categories to the document. Now, we did that in a 2-step process. The first step is the so-called pre-classification. This is what we do on our servers, on our site. And the second part is the training and testing. This is what happens at the Cantech servers, at the so-called Sherpa server. For the pre-classification, in a first step, we created keywords for every category. So keywords for all the 336 categories. We then searched the full text of the documents for those keywords, weighted them, and since machine learning needs a basis of data, we kept only those categories that had at least 50 documents attached to them. Now, with that database, we could go into our actual machine learning system. We imported the data, and through pipelines, algorithms, and neural networks, we vectorized the data using, at the end, Keras model. We got the categorizations by similarity in semantic space. And at the end, we could inspect and even curate those categories. Now, let's take a look into what actually happened. Again, the first step was keyword creation, and this was one of the hardest steps. At the beginning, we were left with 336 categories on the one side and 20,000 documents on the other side, and all that was linking them was the title of the categories. Well, this is a pretty hard point to start, because we were really left with no place of no way of matching those things. Thankfully, we live in modern times, and GPT is a thing for 1.5 years now. And we could leverage this very exciting new technology. GPT has a lot of drawbacks, but what it does in its core is it creates a semantic space around different words and word groups, vectorizes those, and returns similarities. And this is exactly what we needed for our purpose. We had those category names, and we kind of reverse engineered GPT. We told it to give us exactly this semantic space around the keywords. And then we asked it to define other words in this semantic space that define the semantic space. And not only that, but we also asked it to give us a probability of how probable it is that one of those words it returned to us is actually part of that space and not of a different space. What we came up with was a list for all 336 categories, a list of about 40 to 50 keywords, which with their respective probability of belonging to that category. Then, in a second step, we went through the full text of all documents. For every page and every document, we checked for those keywords of the categories. We checked if they're actually on the page, and we weighted them by their probability. And we did that for every page, for every document in our corpus. What we came out with is what you see on the left. It's a result of, in this case, one classified document. And as you can see, we have 3 very dominant categories, and we have a whole lot of weaker categories. Through experimental tests and through through looking at about 200 of those results, we decided that we need a cutoff point for the weaker categories. I mean, it's obvious that even in a text about medicine, you will probably hit maybe a historic keyword or maybe a biological keyword that doesn't make the text genuinely biological or historical. So we cut off the lower keywords. And in the second step, we found that sometimes 1 or 2 categories are very, very dominant towards other categories. In cases like that, we also put in a lower threshold of 30%. So we only categorized, or we only kept categories that had at least 30% of the highest category. Now, with that pre-classification, we then went into our algorithms in our neural networks. We inserted this into the data platform, created machine learning models, let them run. And what you see here is a first preliminary result we got for the 5 main categories in our EUDAT classification. You see humanities and life sciences have quality scores of nearly 80%, which means 80% of the expected predictions are actually returned to us. Sorry. Natural and engineering sciences are weaker, and when we took a look at it, the reason we found is that they're kind of cannibalizing themselves. We have a lot of overlap between those categories, which generates errors and mistakes that we have to account for in a later stage. Social and behavioral sciences consist mostly of document and texts about psychology, which has a big overlap with medicine, and educational texts, teaching texts, which by their nature usually have a second topic next to the education themselves. That is also errors and mistakes we have to account for. What we also learned is that with a greater database, our results got better. So in our latest model, we worked with pretty much the full Humboldt eDoc server with 19,000 documents. What you see here is a quality analysis in 3 different ways. Now you see 3 different bars: precision, recall, and F-score. To keep it very simple, precision is pretty much the quality of a prediction when taking into account wrongly predicted categories. Recall is the quality of the prediction when taking into account missed categories. And the F-score is a measure that takes both into account. So the green bar, the F-score, is the easiest way of defining a quality of a prediction. Now, on the left side here, you see our raw results in the Sherpa platform. We have an F-score of 62%, which means 62% of our predictions are correct. Sherpa, as great as it is not built to work with hierarchical categories, though. So what we did was we inserted a second sample, let the platform categorize it, and compared that sample with our expectations. And in version 1, our expectations were that we wanted the exact category as a result, but we were not taking into account hierarchies, which means if we expected geography, for example, which is a category in the 4th level of our EUDAT hierarchy, and we did not hit it, it usually meant that we didn't hit the upper 3 categories either. That would produce 4 errors while we only expected 1. So in this version, we accounted for this kind of errors, and we raised our F-score by nearly 20% to 80%. So that means this is the actual number we're working with right now. In version 2, we went a step further. The reason we do this is to present it on vivo at the end of the day. And to present it in vivo, we don't need to be perfect. We would like to be, but we don't need to be. If we can classify something in a hierarchical tree, so again, let's say we have geography and we don't predict that it's geography, but we do predict that the text belongs to the natural sciences. Then that prediction is per se not false. And we could actually use that prediction. So version 2 accounts for that fact and shows us how good is our prediction when we take out only the false predictions and assume that every prediction on a tree is correct. And here, you can see down here, we end up at a quality rate of nearly 95%, which is a really good score. Even though those scores are great and we're really, really happy with them, those scores don't predict reality. Those scores only predict our pre-classifications, like they only take into account our pre-classifications and weigh them against what the Sherpa system does. So if our pre-classifications are bad, we would expect Sherpa to probably be even better than our pre-classifications and produce errors. So we have errors on both sides. Missed classifications and over classifications, pretty much good classifications. To check if this system holds in reality, we need expert opinions. To show you that, I show you here a data set of the university in Munich, which also provides an eDoc server, which we could leverage. And similarly to our eDoc server, it comes with keywords, it comes with library categories, and then against those, we hold our predicted categories. Now, this is a very tedious process. Even though we do have abstracts and we do have the full text, we pretty much have to go through every single document with an expert opinion to figure out if the categories we provide are the categories correctly expected. The Sherpa platform assumes the same thing. So when we insert a text in the Sherpa platform, we get our predictions. And the normal workflow would expect us to analyze the document, to delete unfitting categories, and to manually add categories if required. We are a small team, and we are not experts in 336 scientific categories. We cannot do that. So to solve that issue, our idea is an update concept, a running update concept. We need a very good pre-classification, not a perfect one though. If we can provide that, we can train our neural networks and we can classify documents for Vivo. When we re-input them into Vivo, we then have the experts. We have the people who wrote them. We have the people who edited them with access to those documents and their respective classification. And if we're good enough, we hope that those experts will correct for us. And if they do, we can leverage exactly that data to re-import into Sherpa. We will be notified when a classification changes. We can leverage our pipelines, re-import the changes, retrain our neural networks, and at the end, we have a cycle that gets better over time and better with every input by every researcher. Now I would like to hand over to Rolf, who explains how that works with our ontologies. Yeah, Rolf, please. Rolf, you're silent.
So the unmute button is off. Hello, everybody. Thank you, Florian, for the account on our experience in training the machines to automatically determine and classify the semantics of textual artifacts, which of course is just part of the system we were trying to build, a very important part. And as we have seen, it has its challenges and very interesting experiences that we made out of it. I'm gonna go on saying something about how having the opportunity of automatic classification of content plays a role in the bigger picture of a project, of course. So about ontologies, the Vivo platform, the Vivo software is built on ontologies, and it is an open research system built on open linked data. That means what drives it in the backend is our ontologies. And for those who don't know them, ontologies are then formal representations of concepts within a specific domain. So what we're talking about in our case, Vivo represents the American academic domain as an outset. And semantically and structurally relating research entities. This is what Vivo actually does. And in the BUA project, we needed to extend and redefine concepts in these ontologies, in these domains, in order to semantically represent the German academic domain. And this process was informed largely through the production of an organigram or in an institutional organization ontology for the whole alliance. Because the first thing we really needed to know is what are the knowledge domains? And as the alliance, that comprises 4 knowledge domains, the 3 universities in Berlin, and also the Charité, the university hospital, which are in many ways very similar, but also very different domains. So the institutional structures in these domains, they're termed very differently in between. And sometimes also within domains and institutions, they are termed differently. So it is important that each member in the alliance could model their own idiosyncrasies according to their own culture, while still being thematically closely related as they inherit concepts from a common upper ontology, securing a certain degree of computability between institutions. And this is what we're coming to. We want to automate this experience for the end users and for the researchers, in order that much of the tediousness of actually working with documenting and sharing and annotating your research can be automated and easier made. So what we see here is an upper ontology of the Vivo ontology, which is the upper ontology of the whole software. We also created then the BUA upper ontology, which would be, let's say, the overarching model which every ontology under it could inherit in order to have a common degree of computability between them. So there are entities for projects, project outputs, and research results. They have also been updated and extended as we plan to extend the concept of research results and project outputs. Vertically representing the structures, vertically we are representing structures, classes, and relations between them in our domain. But since we have all the idiosyncrasies, ambiguities between the domains, they still remain. And what we are seeing then on a horizontal level is the use of vocabularies and standards, which augment the opportunity of semantically and structurally bridging and relating the institutions and research entities to tighten the possibility of interdisciplinary and cross-institutional discovery. As we see, we are using, so we're planning on using Serif and the research core data sets standards in order to classify project and research results, but also the institutional entities, and also vocabularies like the subject classification from KDSF, the disciplinary classification, and interdisciplinary research fields. So the subject classification is then from Destatis, which is then handed on from KDSF or for the KFID as a standard to mark up the institutional entities in an ontology, in order that we know something about which subject matters we are talking about for these entities. Before I go more into that on how we model these ontologies, I represent the vocabularies and ontologies we are working with and which we have released openly as a result of our project work. Next slide, please. So what we see here is the ontologies that we produced as part of the project. So we produce ontologies for all the organizational structures for the universities. These are then expressed as ontologies and with relations between all the levels from faculty and all the way down to, let's say, chairs and working groups, more or less. This is where it stops and where the project takes off again. We also created then ontology extensions for the German academic domain. There are a lot of terms, of course, missing. A lot of terms were ambiguous from the American domain. We would have faculty, it's not the same in America as in Europe and so on. And then we produced, through the work of the organigrams, we identify a lot of academic terms that needed to be added to the ontology in order that the German Vivo could speak accurately about the knowledge domain. The vocabulary we've been using is, like Florian said, the research discipline from EU.B2Find. We also have the academic subjects from the Statis and the interdisciplinary research field from the KDSF. It's all on GitHub and then all open, available as part of the output of the project. Then next slide, please. Next slide, please. Thank you. So now we get more into the ontology part of it, and I'm going to try to explain what we're seeing here. If we look at the left side, we see the faculties and the institutes and the chairs. That's just a very simplified depiction of the organigram ontology. They inherit, as they are having idiosyncrasies, they have their own names, they have a lot of semantical differences. They inherit then an upper ontology, getting us one step closer to being able to compute that they are more or less similar and that they maybe work with the same things. And it's not enough. So what we see is that we are using then the status here, the academic subject, to say something about what knowledge area or what subject matter does every institutional entity work with? What are they about? This is also not enough, as we have seen, as also Florian talked about. When you have a vocabulary with a lot of words in it, it's very broad. It's very difficult to compute anything on basis of a very broad concept with a lot of words in it. So what we did, we also broke them down, as we did with the ChatGPT. For the classification, we needed to create a semantic space that says something about what is actually this category about. So we would break them down and extract topics from the academic subjects. And these they become part of a vocabulary, let's say an institution-wide vocabulary of topics that describe all the domains within all the 4 universities. Then if you look at the right sides and the middle, after the chair or the working group, what is the first entities will be the projects. And this is where we start classifying a bit differently, because the project is not only about subject matter. Now we get into research. And this is where our 2 vocabularies come into play. It is the EU.B2Find vocabulary, the disciplinary research fields, and the interdisciplinary research fields through the KDSF interdisciplinäre Forschungsfelder vocabulary. And we use them to classify projects and project outputs. And not only textual stuff, but we also would have liked to classify data sets, conference papers. Please go back. Back. Thank you. But at this point, what we can classify are things with text. And again, we need to create the semantic space. So already we have for EU.B2Find, and what we also will have for the KDSF when we go further into the work with the classifications, is the extraction of topics that are related to the categories in the vocabularies, but which can be then related to the project outputs and to the projects and to the system as a whole. So we would end up with a vocabulary with topics which help us to try to bind and bridge the entities within the ontology that are similar but difficult to compute. And this is our idea, and also something we have learned from other projects which have tried to create ontologies for several different institutions and universities, and how that can be done in order to make it as computable as possible and make it as little, so let's say, to create as little work and for the researchers themselves when using the system and when actually using it to express their research or to find other researchers or whatever they want to use the system for. Then next slide, please. Thank you. So what can we do with all this? It's a broader context we're looking for, because it's all about context. And especially when it comes to machines, they are not as good as us to actually understand context. And this is the work we're doing, is trying to give machine a broader context in order that they can help us in automating and computing all these structures for us in order to make our lives a little bit less data, filled with data tasks. Let's put it like that. So one thing is query expansion and refinement. How can we actually find the things in our big system? And the only way we can do this is to create structures that the machine can compute. So with ontology and the vocabulary structures in place, it enables us to expand on the user's search terms, for instance. If you're a researcher, you come to the system and you want to find someone to collaborate with, or you want to understand what kind of resources exist in other projects. You want to understand maybe what other projects are getting funding from, where you also get funding, and what are the outputs they do, and what is the research they're actually doing currently, and so on. So the hierarchical and relational structure of the ontology, it helps to clarify and elaborate the meanings of the terms in the vocabulary, providing them with a context. And each term in the vocabulary represents a concept inherent in the knowledge domain, let's say the ontology, and help disambiguate and ensure consistent understanding across different ontological structures and systems. This has always been a challenge with ontologies and these kinds of technologies. It's identification, as it's based on identifiers. And since the world is big and since there's always new information, the identification of concepts is not always easy to consolidate. And that's why we have to use other structures in order to identify our concepts. So both these sides are crucial for supporting semantic search and functionality as they work together to create a comprehensive machine-readable representation of the domain knowledge, aiming to deliver more relevant and accurate search results to the end user and empowering her to be able to ask the system more complex questions. And this is what is usually needed, because when you come as a researcher to a system, maybe you don't even know the system. So examples for questions that could be asked this system is, for a given institutional unit, find research projects of other units which have addressed the same research problems as I do, or what I see, or what I find in the system. It could be based on the categorization of my research results, find matching research results from other institutions which are categorized within the same research fields. Maybe you need to report also. Now we're getting more into reporting, and impact is important in research. So a funder will also maybe come to the system for a given funder, find other funded projects and their coordinating institution and their project objectives, which are categorized under interdisciplinary research. So as you see, we can ask much more complex questions, having a much more, as a larger context, and larger and more accurate context for the machine to compute. So next slide, please. So to sum up everything, So during our project, we have had the opportunity to get an idea of how far technology at this point can take us in modeling and automating information in knowledge domains. And to ascertain that every technology has its limits, of course, and that we as humans have to accompany it along the way towards greater completeness if we want it to be a greater help to us. We can only come as far as the computer actually understands how to compute. And specifically in this project, it is clear that machine automation still is young, and many data structures, such as vocabularies, are still insufficient for machine computability, as they are constructed for humans, semantically at least, which still perform a superior processing of contextual information still, and can also handle ambiguity, such as overlapping and bundled categories in vocabularies and so on. What is a good step is that we now also have vocabularies in machine-readable formats. This helps a lot, but semantically, as we have seen, we have problems with vocabularies that are not, they are too ambiguous. And this is our challenge. How can we actually teach the machines to understand ambiguity and to dissolve it? So the strength of any system is mostly defined by the quality of its underlying structure and data. And in our case of training the machine to automatically recognize and categorize text, what is showing itself to be crucial is to be the possibility of validating accuracy, validity and relevance of the training sets we feed it. And this is a great challenge, the bigger amount the data is, of course. And it becomes a trade-off between accuracy through manual human intervention and an approximation of accuracy through programmatic validation, as we have seen. We can come this far using the machines to teach the machines themselves. At some point, they need that we take their hands and lead them towards a greater understanding. Of course, transparency and understanding of the tools and algorithms which produce our training sets are important in order to understand the process and how we're going to help the machines to become greater at understanding context. Regarding the GPT, for instance, it's great and it's doing a lot of great things and it has its drawbacks, as also Florian said. But it is difficult to ascertain the validity of the results since GPT is a black box. It does great things, but we don't really know what, unless you are a machine learning expert. And then again, we come back to the manual experts. But as such, the rise of open source LLMs is a positive trend. And I hope we can learn a lot through the use of these and the profilation of these in the academic domains eventually. So it's really important to have sufficient documents, of course, for each category to ensure a balanced training sets. And this is what we have seen also with us. Many of the categories, they have very few documents to represent them. And this is, of course, a challenge. So the bigger and more complex the vocabulary, the broader distribution with the training corpus is needed. This is also what we have learned. So in conclusion of our experience in this project, it is clear that to achieve as a broad as well as accurate model for classification and representation of the domains of human knowledge, there is a need for a human expert intervention on all levels. So the art is, of course, to find the sweet spot where one can use technology to drive and aid the human intervention in incrementally making the machine even more self-sufficient in aiding the humans in our tasks. Next slide, please. With this, we want to acknowledge, of course, Cairntech and their software and their support in our research in the classification. They have been very valuable to us, and it has been an amazing voyage and learning steps, as we call them. So thank you for everybody for being here, and I guess this opens for discussions. Thank you.